Hi, folks. Today we're going to talk about algebraic structures. And so, before we begin, what is algebra? I mean, we've been dealing with algebra our whole lives, but it might be good to give it some context, right? So, thinking of the courses we typically see involving algebra, we have elementary algebra, which introduces the idea of expressions and equations, ways two-dimensional structures and whatnot. It focuses on lines and quadratics, polynomials, radicals, and rationals. But really, it's all about just binary operations. Intermediate algebra then reviews all of those same topics, but it does it all in the language of functions and expands on them a bit. And so we also get new functions, including logarithms, exponentials, and also the relations of conic sections. College algebra then extends it a little bit further. And so it introduces structures and ideas like how about geometric interpretations of relations, matrices, the binomial theorem. You go into things like how do you describe a a parabola in terms of focal points, directrix, things like that. Finally, we have linear algebra. And so linear algebra focuses entirely on the structure of matrices as a way to transform objects in a linear way. So how can we stretch and deform vectors in a way which preserves some form of structure? It's all about matrices. And you may have seen those in college algebra, but this course is a proof-based version of that. What we're going to be talking about is modern algebra, also known as abstract algebra. And so this goes back to the fundamentals of arithmetic, and then it explores the properties of our core number sets. And so what are the properties of the integers? What are the properties of real numbers? And what other structures have those properties? It uses set theory as a foundation, because everything does, but then introduces the idea of a binary operation. And so let's talk about binary operations. This goes way back. What is addition? And so given a set, a binary operation is a mathematical rule which takes two elements and gives you a new element. In the case of numbers, you take two numbers and you get a new number. These are the fundamental tools of arithmetic. And so you know these things. Examples include addition, subtraction, multiplication, division, and exponents. Let's suppose we're dealing with a set of integers. With addition, you take two integers and they give you a new integer. The rule is you combine the quantities together. With subtraction, you take two integers and it gives you a new integer. The rule is you find the difference between the two quantities. With multiplication, again, it's a binary operation. You take two numbers and it gives you a new number. The rule is you repeatedly add a set of numbers some number of times. All of these are binary operations where you're taking two things and getting something new out of them. Division is slightly different, but it's fairly similar. And so if we divide two integers, we are not guaranteed to get an integer. For example, 4 divided by 3 is 4/3, which is not an integer. It's a rational number. If we divide two rational numbers, we will get a rational number, but with one exception, and that exception is 0. And so when we start looking at division and comparing it to some of the other binary operations, we start to notice that there are different rules for different operations and different sets. And so when we're thinking about the properties that we're dealing with, we really need to focus on what the set is and what the operation actually is. Here's another binary operation, exponents. And so much like multiplication represents repeated addition, we use exponents to represent repeated multiplication. We know this. Much like division, we quickly see that the properties for multiplication and exponents are different. And so here are some of the properties for exponents. These are fairly different from the properties which we had for like addition. In this case, we are multiplying two values together and it's the same as adding the exponents. If we divide two values, it's the same as subtracting. Where are these rules coming from? And the thing is, with algebra, we can prove all of these rules fairly easily and determine what all of these extensions mean. Like, what does it mean to have a fractional exponent? What does it mean to have a negative exponent? Those aren't necessarily represented by repeated multiplication, but they seem to form naturally based on how we define our exponents. Another example, maximum and minimum. And so consider the binary operation max of AB, which takes the maximum value of two integers. So the max of 2, 7 is 7. The max of 4 and negative 9 is 4. We could also do the same with minimum. And so the minimum of 2 and 7 is 2. The minimum of 4 and negative 9 is negative 9. What are the properties for these? Are these properties more similar to the exponential properties? Are they more similar to the division properties? Does it depend what set we're dealing with? These are the types of questions we want to start asking when we're dealing with these binary operations. Another example is modular arithmetic. And so consider division by a number. Division is really multiplication in reverse, right? So if A and B are two natural numbers and A is divided by B, then we have the relationship A equals B times Q plus R, where Q is the quotient and R is the remainder. We have that from number theory. That was one of our basic properties or theorems that we had. The quotient Q could be any natural number. The remainder R could be any natural number between 0 and B minus 1. Modular arithmetic is math involving the remainder. And so we define the binary operation A mod B to be the remainder R upon dividing by B. And so 27 mod 4, well, 27 divided by 4 would be 6 with a remainder of 3. And so that means that 27 mod 4 would be 3. 26 mod 7, well, 26 divided by 7 would go 3 times with a remainder of 5. So we have 5. 24 mod 6, well, it goes in evenly. And so the remainder would be 0. And so modular arithmetic, it's a binary operation. We're taking two numbers, we're getting a new number out of it. The question is, what are the properties of modular arithmetic? Are they similar to the properties of addition or multiplication? How can we figure it out? Well, one tool we sometimes use is using tables of values. If we have some small set, we can actually list out all of the different possibilities from binary operations. Usually, we think the multiplication table, but we can do this with any binary operation. The one presented here is an addition table. You don't see an addition table that often, but it's a thing. We're taking two sets, we're determining what the binary operation is doing to values from those sets. When dealing with infinite sets, we can't see all the values, but we can still see a subset if we want to. And so now that we've explored a handful of binary operations, the question becomes, how can we play with them? What type of properties exist? Let's see if we can organically go through some of them. And so we're going to explore a number of different properties of binary operations. Different sets and different operations have different properties. For example, when dealing with natural numbers, A plus B is equal to B plus A always. But A minus B is not equal to B minus A, and there isn't even a guarantee that either is a natural number. In fact, if one is a natural number, there's a good chance the other one isn't a natural number. And so to explore the properties of binary operations, we're going to use this symbol, this asterisk or star, to represent a general binary operation. Now, often we think of the star as multiplication. In this context, we're going to let it mean whatever we need it to mean. It just means that we are doing a binary operation between two things. And so it could mean addition, multiplication, subtraction, division. It could be our min, it could be our max, it could be modular arithmetic, it could be anything. We must also be sure to partner an operation with a set. And so whenever we're talking about a binary operation, we need to be clear about what set we're dealing with. Not all combination of sets and operations have these properties. Our first property is the closure property. And so the closure property says that given a set and a binary operation star, for any two values A and B in the set, A star B must also be in the set. Not all sets and binary operations have the closure property. Let's start with some that do, though. And so addition, multiplication, and subtraction, the integers, is going to have the closure property for all three of those. And so 3 plus 5 is going to give you an integer. 5 minus 22, going to give you an integer. -4 times 19, that will also give you an integer. Division does not satisfy the closure property, at least not under the integers. 12 divided by 7 is not an integer. 12 divided by 0, that's not even a number. And so when restricted to the natural numbers, addition and multiplication satisfy closure, but subtraction does not. So now if we're just dealing with natural numbers, 12 minus 15 is not a natural number. And so we can see the set that we're choosing, it's going to matter quite a bit. The next property is the associative property. The associative property says for A, B, and C in a set, A star B star C is equal to A star B star C, whether you do the A star B first or you do the B star C first. Remember, these are binary operations, and so we're only doing two things at a time. We can't do three things at the same time. And so under addition and multiplication, the integers are associative. 2 plus 3 plus 4 is 2 plus 3 plus 4. It does not matter the order that you are dealing with. Same with multiplication. Under subtraction, the integers are not associative. And so 2 minus 3 minus 4 is equal to -5. 2 minus 3 minus 4 is 3. Those aren't the same value. And so we need to find ways to work around that. If we want to do subtraction and we want to make it so that we can use the associative property, instead we think of negative numbers. And that's one of the big tricks in algebra. Since we want to use the associative property, instead of seeing a subtraction, we will often think of it as adding a negative number. Because 2 plus -3 plus -4 is the same as 2 plus -3 plus -4. At that point, that's addition under the integers, but we can also think of it as subtraction. Similarly, division is not associative. When we need to divide, think of multiplication by fractions. We want to be able to use these properties. And so that's why when we're dealing with algebra, we want to think of alternative ways to approach things like subtraction and division. The identity property. And so the identity property states that for a given set and binary operation, there's an element E, such that A star E is equal to E star A is equal to A. We call E the identity element. And be aware this E is not Euler's number. This isn't the 2.7 number we know. Instead, we're just using this as a placeholder, and it's a common placeholder for the identity element. Often, your identity element is going to be either 0 or 1. Not always, but often. And so the integers under addition have an identity element of 0 because you can add 0 and it doesn't change anything. The integers under multiplication have an identity element of 1 because you can multiply by 1 and it doesn't change the value. Under subtraction and division, we don't have an identity element. It's only under addition and multiplication. There may be other binary operations which satisfy the identity element, but when we're talking about these four, it's just addition and multiplication. The inverse property. So the inverse property states that for a given set and binary operation, for any value in the set, there's going to be an inverse element in the set, such that or if you do A star, the inverse of A, that's the same as A, or the inverse of A times A, which is just equal to E, where E is the identity element. We call this A prime the inverse. And so the integers under addition satisfy the inverse property, where for any value A, we would say that the inverse is going to be negative A. And so 3 plus negative 3 equals 0. Negative 3 plus 3 equals 0. The integers under multiplication do not satisfy the inverse property, but the rational numbers without 0 do. And so any rational number A has a value 1 over A, such that A times 1 over A is equal to 1 over A times A is equal to 1. If you have 2/3, well, 2/3 times 3/2 is equal to 3/2 times 2/3 is equal to 1. So we're just using the reciprocal. This only works as long as A is not 0. So we would have to make sure that we restrict our set to not include 0. We can't take 0, multiply it by something, and get 1. The next big property is the commutative property, and this is one we all feel a little bit more comfortable with. Commutative property says that if you have A star B, it is the same as B star A. This works great for addition and multiplication. So 14 plus negative 3 is the same as negative 3 plus 14. 12 times 5 is the same as 5 times 12. This does not work for subtraction. This does not work for division, at least not on the integers. Our next one's a little different, the distributive property. The distributive property requires 2 operations. And so we typically use multiplication and addition to represent the 2 binary operations because that's where we see the distributive property most often. And so the distributive property states that for a given set and operations addition and multiplication, it must always be true that A times B plus C is equal to A times B plus A times C. We use this property a lot in algebra because this is the only one which connects addition and multiplication. As an example, 6 times 7 plus 8 is the same as 6 times 7 plus 6 times 8. Both are going to give you 90. Note, if the set isn't commutative, the distributive property described is considered the distributive property from the left. And we also have a distributive property from the right, which would say B plus C times A is B times A plus C times A. This pops up when you're dealing with matrices, because for matrices, we do have the distributive property, but we do not have commutativity. Some more properties are the properties of equality. And we have to be careful because when we're thinking about this, equality isn't as much a binary operation. And so when dealing with equations, we have the properties of equality. And the first 3, reflexivity, symmetry, and transitivity, that's how we defined equality. Remember, an equivalence relation is a relation which is reflexive, symmetric, and transitive. And so those are the core of being an equation. From there, we have all of these other properties, the addition, subtraction, multiplication, and division. Those are often called the properties of equality, where if A is equal to B, then A plus C is equal to B plus C. They all kind of originate from this idea of substitution. If A is equal to B, then B can replace A in any expression. And so if you have A plus C, that's the same as B plus C. If we're saying A is equal to B, we can replace the A with B. Note the equality is not a binary operation because it doesn't take 2 numbers and give you a new value. Instead, it's more of a, hey, this is a true thing, and that's how it works. Applications of algebraic properties. I mean, there are a lot of applications. Arithmetic, pre-algebra, elementary algebra, and intermediate algebra are just explorations of the properties of real numbers. And so we just described the properties that describe all real numbers. You have your closure, you have your associativity, commutativity, your identity, your inverse, and your distributive property. The entirety of arithmetic, pre-algebra, algebra 1, and algebra 2 are just applying those core properties. And so linear functions, polynomials, rational functions, radical functions, exponential functions, logarithmic functions, conic sections, these are all objects built on binary operations and their properties. All of it. And so everything that you have done related to algebra or arithmetic is applications of these algebraic properties. And so it's good to know these algebraic properties. You've already done all of the applications, whether you knew it or not. Next big piece is we're going to start putting some of these properties together to create algebraic structures. And there's a variety of different algebraic structures out there. And so in modern algebra, we explore a variety of different types of sets and binary operations and search for deeper understanding. While simple structures can be modeled using our core number sets, we can also model things like rotations, symmetries, and other more abstract objects. One of the common ones is the Rubik's Cube. The Rubik's Cube can be modeled using the algebraic structures. It turns out it's going to satisfy closure, it's going to satisfy associativity, it's going to satisfy the identity and the inverse property. And that makes it so that we can apply a lot of our understanding of algebraic structures to a Rubik's Cube. Our most basic sets, or our most basic algebraic structures, are that of the monoid and the group. And so a monoid is a set with a binary operation which satisfies three properties: closure, associativity, and identity. A group has four properties: closure, associativity, identity, and inverse. If it also satisfies the commutative property, we would say it's an abelian group. So abelian group. This group, it's fairly well structured at that point. We can think of this as having a similar structure to the integers under addition. The next two involve two operations, and so they would be rings and fields. And these are much more complicated structures. But again, these are the structures which we see every day. And so a ring is a set with two binary operations which satisfies all of these properties. So closure under addition, associativity under addition, identity under addition, inverse under addition, commutativity under addition. So that means it's an abelian group under addition. And then it also satisfies closure under multiplication, associativity under multiplication, and it's both left and right distributive. And so it doesn't have to be commutative under multiplication. It doesn't have to have an identity or inverse under multiplication, but that's what it takes to be a ring. A field is a ring which additionally satisfies the following. And so it's commutative under multiplication. It has an identity and an inverse under multiplication, except possibly at zero. Essentially, a field is an abelian group under both addition and multiplication, and it has the distributive property. It is a very highly structured set, and it describes some of our most common number sets. And so let's explore all of our number sets through this new language. And so the whole numbers under addition form a monoid, but they do not form a group. And so the whole numbers, remember, it starts at zero and goes on to infinity, just using counting numbers. So associativity and closure, no problem. And there's an identity element that has zero. And so there is no additive inverse, though, because the whole numbers do not include negatives. If you wanted to get from 7, add something, and get back to 0, we could not do that using just the whole numbers. The natural numbers are not even a monoid because they do not have the identity element. If we wanted to make it so the whole numbers were a group, we would need to expand them to be the integers. And so the integers are going to be an abelian group because they satisfy the commutative property and they also have the additive inverse. And so the integers are our standard example for an abelian group under addition. The integers under addition and multiplication form a ring, but do not form a field. And so as an abelian group under addition, all that's needed to be checked is the multiplicative properties and distributive properties. Well, if we think about a field, and let's go back up, a field would include commutative under multiplication, identity under multiplication, and inverse under multiplication. Well, we don't really have an inverse under multiplication when we're talking about the integers because we need fractions. We do have associativity though. We certainly have closure. For this reason, the integers are not a field because they do not include multiplicative inverses. If we wanted to extend it to be a field, well, we would need to make them rational numbers. And so the rational numbers under addition and multiplication form a field. So do the real numbers. And so whole numbers are a monoid. Integers are an abelian group. The integers are also going to be a ring, and the rational numbers are a field. And so when we start thinking about the structures that we're dealing with, these are highly structured number systems, and now we have a way of understanding what that structure actually looks like. We knew the structure of the primes, but now we understand how binary operations can describe the set as well. Here's another example. Let's say that we are taking the maximum of two numbers, and let's say that we are restricting it to the integers from -10 to +10. Well, this set is closed because the maximum of two numbers between -10 and 10 is definitely going to be between -10 and 10. The set is associative. The max of three numbers will be the largest of the three, regardless of which two you take first. Similarly, the set is commutative because the order doesn't matter. There's even an identity element, -10. The max of -10 and any number a is that a value itself. What it does not satisfy is it does not satisfy the inverse property. Given the max of 5 and a, there's no way that we can get it to be back to the -10. The maximum would be at least 5, so we're stuck there. Since there's no inverse, this is a monoid. It has a similar properties to the whole numbers under addition. And so how would this be different if the set was instead all the integers? Well, if instead of dealing with just integers from -10 to +10, if we dealt with all of the integers, I don't think we would have an identity element anymore. Unless we choose -infinity as our identity element, but that might not work so well. The Klein 4 group is a little bit more exotic, and we're going to see some more exotic groups soon. Sometimes we explore more abstract structures, and here is a structure with, you can see our asterisks representing our binary operation, and this is a table of values, and so I star I is I, X star X is I, Y star Y is I, Z star Z is I is our identity element. When we take X times Y, we get Z. When we take Y times Z, we get X. When we take Z times X, we get Y. And so anything times itself for this particular set is always going to give you I, but if you take any two different things, you're going to get whatever the third value is. And so X times Y is Z, Y times Z is X, Z times X is Y. Anything times I is just going to give you that same anything. This is commutative. I mean, we can see X times I is X, I times X is X. This is going to form an abelian group under the which is called the Klein 4 group. It has an inverse because every value is its own inverse in this situation. While numbers might not satisfy the conditions of X, Y, and Z, it gives us a framework for other groups. And so this is now some structure which is not tied to our number structure. And that can be very useful. Our next set is called the quaternions. And this is another group. And so consider the set with 8 values, 1, -1, I, -I, j, -j, k, and -k. And a multiplication table as described to the right. This set and operation form a group called the quaternions. This is kind of a weird looking thing. You can see that it's got an identity element, which is 1. And then we also have the -1. Well, -1 times -1 gives us 1. That's promising. But if we take I, j, or k, or any of the others, and multiply them by themselves, you end up getting -1. If we wanted to get to 1, we would have to do I times -I. Essentially, I, j, and k are working as though they are each complex numbers, because I times I is -1, j times j is -1, k times k is -1. And this is kind of an odd structure, but it's a very useful structure. And so when we think about imaginary numbers, what imaginary numbers do extremely well is they model rotations. Having I, j, and k, we are actually able to model three-dimensional rotations very clearly. And this becomes an essential tool when we're talking about physics and engineering. And so if you want to model how something is actually moving, we can use this group, the quaternions, in order to model those rotational movements. Another example of a group is the rotations of a cube. And so from an initial position, we can rotate a cube along any of its 3 axes. But some rotations can be defined in terms of other rotations. For instance, if you rotate clockwise 4 times, you're going to get back to your starting position. If you rotate clockwise going around some other central axis, you're also going to get that it repeats every 4 times. And so it turns out that with the rotations of a cube, it satisfies the associative property. It doesn't matter the order with which you are doing these rotations as far as which pairs of rotations you do first. There's also an identity rotation, which involves just not rotating at all. And any rotation can also be rotated back. And so the set of rotations of a cube turns out to be a group. We've satisfied closure, we've satisfied associativity, we've got the identity, and we've got the inverse. And so whenever we're thinking of how we rotate an object, it is a group. Another common example is the movements of a clock. Consider the hour hand of a clock. 2-hour positions can be added together and give you a new hour position. 5 plus 4 is 9. 11 plus 3 is 2. Consider, are these motions satisfy the associative property and commutative property? There's an identity element in the form of 12. In this case, if you add 12 to anything, you're going to be back to your starting position. And every number has an inverse, which gives 12. So for instance, 5 and 7 would be inverses. This means that the motions of a clock form an abelian group. Another example is matrices in linear algebra. So matrices are a tool often introduced in college algebra or pre-calculus, and then gone far more in depth when you enter into linear algebra. What it is, if you've never seen a matrix before, is it's just an array of numbers. But what's interesting is the way that we multiply these things, we go across in the first one and down on the second one. And so to multiply 2 matrices, this element here comes from A11 times B11 plus A12 times B21. And we can do that for all of the other elements in here. So notice we have something with 3 rows and 2 columns. We're multiplying it by something which is 2 by 2, and we're getting another one which is 3 rows and 2 columns. Matrix multiplication is a little bit tricky, and it turns out it's not commutative. And so while it satisfies a number of different properties, it's not commutative, which means we're going to get a non-abelian group out of matrix multiplication. It's kind of fun. Final thoughts. In arithmetic, we often focus on the numbers, while in elementary and intermediate algebra, we often focus on the variables. The thing that unites both is the properties. And really, everything in algebra, everything in arithmetic, it's all just boiling down to understanding how these properties work. When we consider sets and their properties, we get a new collection of structures, which we can use to explore the world around us. When presented with a new structure, it's important to explore what properties it has. These ideas and structures can be greatly generalized. A binary operation is just a thing that takes two things and makes something new. Mixing eggs and flour is a binary operation on food. Is food a group? What would the identity element be? And so these are the types of questions you want to start asking yourselves. Binary operations are such a general thing. The idea of taking two things and getting something new. Just about everything we're doing, anytime we're making some form of connection, we are combining things. How are we doing it? And so how do you use binary operations in your life? How do you combine things together to make something new? With that, I'll let you get to work exploring where you find binary operations and algebraic structures in the real world. Good luck, folks.